The enigma of the neutrino, the ghost particle of the cosmos illuminating stars and dark matter. The universe, a tapestry woven from forces and particles we strive relentlessly to comprehend, harbors within its vast expanse entities so elusive, so ethereal, that they defy conventional observation, earning them the poetic yet profoundly accurate moniker of ghost particles, the neutrinos. These fundamental constituents of matter, predicted theoretically in 1930, a concept initially fraught with skepticism and later confirmed through painstaking experimental endeavor, represent a cornerstone of modern particle physics, an invisible messenger carrying pristine information from the most violent and inaccessible corners of the cosmos, ranging from the fiery infernos of collapsing stars to the very fabric of the early universe, and potentially holding the key to unlocking the greatest mystery of modern cosmology, the nature of dark matter. To fully appreciate the profound significance of the neutrino, one must embark on a journey tracing its lineage, exploring its bizarre characteristics, and charting the revolutionary impact of its discovery and subsequent study across astrophysics, particle physics, and even the burgeoning field of astroparticle physics. The genesis of the neutrino concept lies rooted in the perplexing observations surrounding beta decay, a form of radioactive decay where a neutron within an unstable atomic nucleus transforms into a proton, emitting an electron, traditionally known as a beta particle, and an antineutrino. When physicists in the early 20th century meticulously measured the energy spectrum of these emitted electrons, they encountered a significant anomaly. Conservation of energy, a bedrock principle of physics, seemed to be violated because the resulting electrons exhibited a continuous spectrum of kinetic energies, rather than a discrete, fixed value that would be expected if only two particles, the nucleus and the electron, were involved in the decay process. If the energy were not conserved, it implied that some energy was simply vanishing, a truly unacceptable proposition for the scientific community grappling with the foundations of reality. In 1930, Wolfgang Pauli, in a moment of inspired, almost desperate conjecture, proposed the existence of a third, hitherto unseen particle, which he initially termed the neutron, a term later reserved for the heavier particle found in the nucleus, before settling on the diminutive o neutrino, meaning little neutral one, emphasizing its supposed lack of electric charge. Pauli posited that this neutral, nearly massless particle carried away the missing energy, thus preserving the sacred laws of conservation of energy and momentum. The brilliance of Pauli's hypothesis lay not just in solving an immediate crisis but in introducing a particle so weakly interacting that its direct detection seemed almost impossible, a prediction that held true for nearly 3 decades. The theoretical construct of the neutrino was solidified and expanded upon by Enrico Fermi in the mid-30s, who developed a robust, mathematically consistent theory of beta decay incorporating Pauli's ghostly particle, establishing the framework for the weak nuclear force, one of the 4 fundamental interactions governing the universe. The weak force, distinct from the strong nuclear force that binds quarks into protons and neutrons, and the electromagnetic force which governs light and chemistry, is responsible for particle transformations, including radioactive decay and, crucially, the thermonuclear processes powering stars. The weak interaction is mediated by massive force-carrying particles, the W+, W-, and Z bosons, discovered experimentally in the 1980s at CERN, an extraordinary confirmation of the standard model of particle physics. Because these mediating bosons possess substantial mass, the range of the weak force is extremely short, making the interaction probability, the likelihood of a neutrino interacting with any other matter, incredibly small, justifying Pauli's initial apprehension about its detectability. The definitive proof of the neutrino's existence arrived in 1956, thanks to the pioneering work of Clyde Cohen and Frederick Reyners, who employed a massive detector near the Savannah River plant, capitalizing on the intense flux of antineutrinos produced by the nuclear reactors operating there. They observed the characteristic signature of inverse beta decay, where an antineutrino strikes a proton, resulting in a neutron and a positron, the antimatter counterpart of the electron. The painstaking verification of this signal, involving careful shielding and correlation with reactor activity, marked one of the most triumphant validations in the history of experimental physics, finally pulling the neutrino from the realm of theoretical necessity into tangible reality. However, the story of the neutrino only grew more complex and fascinating with the subsequent realization that there were not just 1, but 3 distinct flavors or types of neutrinos, corresponding perfectly to the 3 known charged leptons, the electron, the muon, and the tau. These are the electron neutrino, the muon neutrino, and the tau neutrino, each associated with its respective charged partner particle. This triad forms the lepton sector of the Standard Model, a triumph of theoretical symmetry. Yet, the greatest shock regarding the neutrino family was yet to come, fundamentally altering our understanding of particle identity. The turning point arrived in the late 20th century with the realization of neutrino oscillation. If neutrinos were strictly massless, as the initial Standard Model predicted, flavor conservation dictated that a neutrino produced as, say, an electron neutrino, must remain an electron neutrino forever. However, experiments observing neutrinos traveling vast cosmic distances began yielding perplexing results. The Sudbury Neutrino Observatory, or SNO, in Canada, which utilized heavy water to detect all three flavors of neutrinos emanating from the Sun, provided the clincher. Solar neutrinos, produced via fusion deep within the solar core, a process heavily reliant on the weak force, should theoretically arrive at Earth predominantly as electron neutrinos. SNO's precise measurements confirmed the total solar neutrino flux, matching theoretical predictions remarkably well, but demonstrated that only about one-third of them were electron neutrinos upon arrival. The rest had transformed into muon or tau neutrinos during their 8-minute journey through space. This phenomenon, neutrino oscillation, irrefutably proves that neutrinos possess mass, albeit extremely tiny masses, and that they can morph between flavors as they propagate. This discovery shattered the rigid symmetry of the original Standard Model, necessitating an expansion to accommodate non-zero neutrino masses, a development that earned the researchers behind these observations the Nobel Prize in Physics in 2015. The implication of neutrino mass is profound. In the Standard Model, all fundamental particles are assumed to be either massless or to acquire mass through the Higgs mechanism. Neutrinos do not fit neatly into this paradigm, suggesting physics beyond the Standard Model, a realm where the elegant simplicity of the current framework breaks down. Current experimental efforts are dedicated to measuring these minuscule masses with ever-increasing precision. While direct measurement of the absolute mass scale remains elusive, experiments like the Karlsruhe tritium neutrino experiment, or CATRIN, which measures the endpoint of the tritium beta decay spectrum, place stringent upper limits on the electron neutrino mass, currently suggesting it is less than 1.0 electron volts, a mass so small it is billions of times lighter than the electron. The pattern of these masses, the so-called neutrino mass hierarchy, whether the mass differences are normal or inverted, remains a significant open question guiding next-generation experiments. The cosmic role of neutrinos extends far beyond terrestrial laboratories. They are the quintessential messengers from extreme astrophysical environments, acting as a direct, nearly unadulterated probe of processes shielded from electromagnetic radiation. The most prolific source is, undeniably, our own Sun. The solar neutrino flux provides a real-time confirmation of the Standard Solar Model, the theoretical framework describing the Sun's structure, energy generation via the proton-proton chain reaction, and its evolution. The initial solar neutrino problem, resolved by the observation of oscillation, forced refinements in our understanding of solar physics, particularly the temperature gradient and density profile within the core. Moving beyond the solar system, neutrinos become messengers from catastrophic cosmic events. When massive stars, those exceeding roughly 8 times the mass of the Sun, exhaust their nuclear fuel, their iron cores collapse under immense gravitational pressure, leading to a core collapse supernova. This event releases an astonishing torrent of energy, approximately 99% of which is carried away not by light, but by neutrinos. In a matter of seconds, a supernova emits more neutrinos than all the stars in the observable universe combined will emit photons over their entire lifetimes. The detection of the 9860 neutrino burst, SN 1987A, originating from the Large Magellanic Cloud, stands as one of the greatest experimental achievements in astrophysics. Detectors like Kamiokande 2 in Japan and the Irvine, Michigan Brookhaven experiment in the United States registered a handful of these particles, a fleeting glimpse that confirmed the long-held theory of core collapse as the mechanism driving these stellar explosions and provided the first direct observational evidence of the neutrino emission from an external galaxy. The slight time delay between the initial photon arrival and the neutrino detection allowed astrophysicists to place constraints on the difference between the speed of light and the speed of neutrinos, proving them to be virtually identical, reinforcing the notion that neutrinos travel at speeds extremely close to that of light. The study of high-energy astrophysical neutrinos, those with energies reaching megaelectron volts and beyond, opens the door to PeV astronomy, a field rapidly maturing thanks to observatories like the IceCube Neutrino Observatory situated deep within the Antarctic ice sheet. IceCube, functioning as a kilometer-scale Cherenkov detector buried under tons of transparent ice, is designed to capture the faint blue light emitted when high-energy neutrinos interact with the ice, producing secondary charged particles. In 2017, IceCube made a landmark discovery, the identification of a high-energy neutrino, designated IceCube 1711-03, which coincided spatially and temporally with a powerful flare emanating from a distant blazar, TXS 0506+056, a supermassive black hole actively accreting matter at the center of a galaxy millions of light-years away. This event provided the first direct evidence linking a specific active galactic nucleus to the production of cosmic rays, the high-energy protons and atomic nuclei that bombard Earth. Since neutrinos interact so weakly, they travel undeflected by intergalactic magnetic fields, allowing them to point back to their sources with unparalleled accuracy, unlike charged cosmic rays whose paths are scrambled across the galaxy. This discovery inaugurated the era of multi-messenger astronomy, combining gravitational waves, electromagnetic radiation, and neutrino detection to study the universe's most energetic phenomena. The search for ultra-high-energy neutrinos, possibly reaching energies far exceeding those produced in known accelerators, continues, pushing the boundaries of detector technology. These extreme energy particles might originate from exotic sources such as gamma-ray bursts, or perhaps even from hypothetical environments like the decays of supermassive dark matter particles or relics from the very earliest moments of the universe, often referred to as the cosmological neutrino background, analogous to the cosmic microwave background radiation but composed of neutrinos. The cosmological neutrino background, or CNUB, is one of the most compelling, yet currently experimentally unreachable, relics of the Big Bang. Theory predicts that a sea of neutrinos, left over from the epoch when the universe was only a few seconds old and still hot and dense enough for neutrinos to interact readily, permeates all of space. As the universe expanded and cooled, neutrinos decoupled from the rest of the matter and radiation approximately 1 second after the Big Bang, traveling freely ever since. Due to the universe's expansion, these ancient neutrinos are now incredibly cold, possessing extremely low kinetic energies, estimated to be around 1/10 of an electron volt. Detecting these ultra-low energy, ghost-like particles directly is an immense technological challenge, far beyond current capabilities, as the required detector volumes and sensitivity levels are astronomical. However, their collective gravitational influence on the large-scale structure of the universe, particularly the clustering of galaxies and the clustering of the cosmic microwave background anisotropies, provides indirect, but robust, evidence of their existence and places crucial constraints on their total mass density, offering a powerful cosmological test of the Standard Model. This brings us to the nexus where neutrino physics intersects with the darkest puzzle in cosmology, dark matter. Dark matter constitutes approximately 85% of the total mass budget of the universe, yet its fundamental nature remains entirely unknown, representing a profound gap in our physical understanding. The prevailing theory suggests dark matter is composed of yet-to-be-discovered, weakly interacting massive particles, or WIMPs, which interact via gravity and possibly the weak nuclear force. Neutrinos, while weakly interacting, are known particles, and they are decidedly not the primary component of dark matter. They possess mass, yes, but their mass is far too small, and their energy distribution too hot, meaning they move too fast relative to the speed of light for the early universe constraints, to account for the observed structure formation. The universe observed is one where structure, galaxies, clusters, formed relatively early, implying that the majority of the unseen matter must have been colder in the early universe, moving slowly enough for gravitational collapse to begin unimpeded. Neutrinos, being relativistic in the early universe, are categorized as hot dark matter, and while they contribute a small fraction to the total mass density, they are insufficient to explain the observed gravitational scaffolding. However, neutrinos might offer tangential clues or even be a secondary component within a broader dark matter hypothesis. The fact that neutrinos have mass confirms physics beyond the Standard Model, suggesting new symmetries or mechanisms for mass generation, which might operate similarly for the actual dark matter particle. Furthermore, if a hypothetical, heavier, sterile neutrino exists, a neutrino flavor that interacts only via gravity and potentially mixes with the known active neutrinos, it could potentially qualify as a component of cold dark matter, or at least a warm component. The search for sterile neutrinos, often hypothesized to be mediators of the neutrino mass mechanism via the seesaw mechanism, a complex theoretical construct where the very light mass of active neutrinos is explained by the existence of extremely heavy, sterile counterparts, is an active front in experimental physics. Utilizing techniques like looking for unexplained X-ray signals from galactic centers or searching for the decay signatures of these heavy particles in underground detectors. The exploration of neutrino properties, particularly their mass differences and CP violation potential, is intertwined with the question of baryogenesis, the mechanism that created the observed asymmetry between matter and antimatter in the cosmos. The Standard Model, while incredibly successful, cannot account for the matter-antimatter imbalance. The observed CP violation within the Standard Model, primarily observed in the quark sector through K and B meson oscillations, is insufficient by several orders of magnitude to explain the survival of matter after the Big Bang. Neutrinos, through their oscillation behavior, present the tantalizing possibility of significant charge parity, or CP, violation in the lepton sector. If CP violation is observed in neutrino oscillations, meaning that the probability of a neutrino oscillating into another flavor differs from the probability of its antiparticle counterpart oscillating, it could provide the necessary engine for leptogenesis, a theoretical process where CP violating processes involving heavy neutrinos in the early universe generated a lepton asymmetry, which was then converted into the observed baryon asymmetry through electroweak processes known as the Sphaleron mechanism. Experiments like T200, located at Fermilab, are specifically designed to measure the differences between neutrino and antineutrino oscillation probabilities over long baselines to probe this potential CP violation, a discovery that would revolutionize our understanding of why the universe exists as it does, filled with matter rather than being an abyss of equal parts matter and antimatter. The sheer scale and dedication involved in neutrino detection underscore the difficulty of observing these particles. Current flagship experiments rely on monumental engineering feats. Superkamiokande in Japan, a massive detector holding 50,000 metric tons of ultra-pure water, operates deep underground to shield against cosmic ray interference. It detects the Cherenkov radiation, a faint blue flash produced when a charged particle moves faster than the speed of light in that medium, generated when a neutrino scatters off a water molecule, producing an electron or muon. The precision required is staggering. The water must be purified to an extent that removes nearly every impurity, as contaminants can quench the faint light signal. Similarly, experiments designed to probe the elusive three-flavor mixing scheme, such as the Deep Underground Neutrino Experiment, or DUNE, planned for construction across the United States, will use liquid argentine projection chambers to achieve unparalleled sensitivity in measuring oscillation parameters, sending intense neutrino beams over distances exceeding 1,300 kilometers to detect how the beam changes flavor en route. The study of neutrinos, therefore, is not a singular scientific pursuit but a converging field linking nuclear physics, particle physics, cosmology, and astrophysics. They serve as historical artifacts, carrying signatures from the Big Bang, as astrophysical tools, mapping the interior of stars and pinpointing active galactic nuclei, and as guides pointing towards physics beyond our current theoretical consensus, particularly concerning mass generation and the baryon asymmetry puzzle. Consider the implications for stellar evolution again. While the Sun's neutrinos confirm our steady-state model, neutrinos from exotic stars like magnetars, neutron stars possessing magnetic fields trillions of times stronger than Earth's, or those involved in the formation of stellar mass black holes, carry signatures of extreme physics inaccessible by electromagnetic observation. The precise energy spectrum of neutrinos emitted during the accretion phase of a black hole or the formation of a protoneutron star gives us direct insight into the equation of state of ultra-dense matter, probing nuclear physics at densities far exceeding that of an atomic nucleus, where matter is compressed into a state governed by quantum chromodynamics under extreme conditions. The equation of state, relating pressure to density in such an environment, is notoriously difficult to determine experimentally. Stellar collapse neutrinos provide a unique astrophysical laboratory for testing these theoretical models. Furthermore, the potential for relic neutrinos from past supernova events occurring within our own Milky Way galaxy, even if billions of years old, presents a theoretical possibility for detection, albeit with current technology remaining far below the required sensitivity. If a supernova occurred relatively nearby, say within 10,000 light-years, the sheer number of neutrinos produced might allow for a statistically significant, albeit extremely faint, signal to be registered by next-generation, even larger volume detectors than those currently operational, offering a probabilistic window into the history of our galaxy's stellar deaths. The pursuit of understanding the neutrino's mass hierarchy, whether the heaviest neutrino mass eigenstate is the tau neutrino or the electron neutrino, is also critical for understanding lepton number conservation. If neutrinos are their own antiparticles, known as Majorana particles, rather than distinct from their antiparticles, which are Dirac particles, the underlying physics changes dramatically. This possibility is explored through the search for neutrinoless double beta decay, a hypothetical rare decay process where two neutrons decay simultaneously into two protons and two electrons without the emission of any neutrinos. Observing this decay would confirm that neutrinos are Majorana particles and would provide a concrete experimental pathway to constrain the absolute neutrino mass scale, potentially confirming the seesaw mechanism. While no convincing evidence for this ultra-rare decay has yet been found, the sensitivity of experiments like Gerda and Cure continues to push the lower bounds on the half-life of this process to over 10 to the 26th power years, placing immense pressure on theoretical predictions derived from nuclear structure calculations. In summary, the neutrino, the particle born of a necessary mathematical fix, has evolved into a cornerstone of 21st century physics. From the confines of nuclear reactors to the heart of collapsing stars, these ghost particles travel unimpeded, carrying the least spoiled records of cosmic evolution and fundamental physical laws. Their oscillation reveals that mass is present where none was predicted, hinting at mechanisms beyond the standard model. Their detection connects us directly to the energetic violence of supernovae and the mechanisms driving galactic evolution. The ongoing quest to precisely measure their masses, determine their nature as Dirac or Majorana particles, and harness their observational power promises not only to refine our current cosmological models but perhaps, finally, to illuminate the nature of the invisible majority of the universe, dark matter, or, failing that, to chart an entirely new, previously unimagined landscape of fundamental physics waiting just beyond the reach of our current, yet ever-improving, sophisticated instruments. The enigma persists, but every faint flash of Cherenkov light, every recorded oscillation shift, brings humanity one step closer to understanding the deepest secrets whispered by these universe-spanning, nearly undetectable messengers. The journey into the subatomic realm, guided by these spectral particles, confirms that the universe is far richer, stranger, and more interconnected than our initial, classical descriptions allowed, perpetually demanding greater ingenuity and deeper theoretical leaps.